Hello friends, welcome to today's topic, which is clustering through the k-means algorithm. K-means is a powerful unsupervised machine learning algorithm used for predicting groups within an unlabeled dataset. Its objective is to divide data into clusters, making similar data points part of the same group. The algorithm initializes cluster centroids and iteratively assigns data points to the nearest centroid, updating centroids based on the mean of points in each cluster using the Euclidean distance measure. Let's assume a banking dataset with two variables describing each customer, their income and amount of debt, and the bank wants to use this data to perform customer segmentation. The first step is to visualize it as a scatter plot with income on the x-axis and debt on the y-axis. Here we can clearly visualize that these customers can be segmented into 4 different clusters. This is how clustering helps to create segments from the data. The bank can further use these clusters to make strategies and offer discounts to its customers. This leads us to the properties of these clusters. If the customers in a particular cluster are not similar to each other, then their requirements might vary, right? If the bank gives them the same offer, they might not like it, and their interest in the bank might reduce. So this is not an ideal situation. Having similar data points within the same cluster helps the bank to use targeted marketing. The second important property of clusters is that the data points from different clusters should be as different as possible. The image shown in this slide would help us understand this point better. In this first case, the points in the first and second clusters and the third and the fourth clusters are visibly not as far away as to make these clusters truly differentiable. While in the second case, we can see that the points in the different clusters are quite far away as compared to the first case. And finally, in this third case, the points in the clusters are as far away as possible, but the drawback here is that we only have 2 clusters, which is a bit too less for making a marketing strategy. Now, clustering is a widely used technique in a large number of industry verticals. One of the most common applications of clustering is customer segmentation, which we already covered in the previous slides. And it isn't just limited to banking. This strategy is across the industry verticals, such as telecom, pharmaceuticals, e-commerce, restaurants, etc. Clustering also helps in segmenting similar documents using their properties. We can also use clustering to perform image segmentation, where we try to club similar pixels in the images together. And finally, clustering can also be used in recommendation engines. Now, there are 2 evaluation metrics for clustering to assess the goodness of a given clustering model. The first one is inertia. Recall the first property of clusters we covered in a previous slide, that all the data points in a cluster should be similar to each other. This is what inertia evaluates. It tells us how far the points within a cluster are. It calculates the sum of distances of all the points within a cluster from the centroid of that cluster. We calculate this for all the clusters, and the final inertia value is the sum of all these distances. This distance within the clusters is known as intra-cluster distance. So inertia gives us the sum of intra-cluster distances. And the smaller the inertia, the better it is. Now, inertia makes sure that the first property of clusters is satisfied, but it doesn't care of the second property, that different clusters should be as different from each other as possible. Along with the intra-cluster distances, the Dunn index also takes into account the inter-cluster distances, that is the distance between the centroids of two clusters. The Dunn index is the ratio of the minimum of inter-cluster distances and the maximum of intra-cluster distances. We want to maximize the Dunn index. The more the value of the Dunn index, the better the clusters will be. Let us understand the intuition behind it. In order to maximize the value of the Dunn index, the numerator should be maximum. Here we are taking the minimum of the inter-cluster distances, so the distance between even the closest clusters should be more, which will eventually make sure that the clusters are far away from each other. On the other hand, the denominator should be minimum. To maximize the Dunn index, we take the maximum of all intra-cluster distances. The logic is that the maximum distance between the cluster centroids and the points should be minimum, eventually ensuring that the clusters are compact. Since we have been talking about the Euclidean distance measure, a word here about the calculation of it. When we implement the k-means algorithm using Python, we won't have to manually calculate the distances, but it is good to know the formula. It is the root of sum of squared differences of the features of the two observations, as you can see in this slide. How to apply k-means clustering algorithm? Let's say we have these 8 points and we want to apply k-means to create clusters for these points. Here is how we can do it. The first step is to pick the number of clusters k. Next, we randomly select the centroid for each cluster. Let's say we want to have 2 clusters, so k is equal to 2. How to initialize the centroids? One way is to randomly pick 2 points. Another method is through scatter plot observation. Here, the red and green circles represent the centroids for these clusters. Once we have initialized the centroids, we assign each point to the closest cluster centroid. Here you can see that the points closer to the red point are assigned to the red cluster, whereas the points closer to the green point are assigned to the green cluster. Now, once we have assigned all of the points to either cluster, the next step is to compute the centroids of newly formed clusters. In the second image, the red and green crosses are the new centroids. Then the steps 3 and 4 are repeated. So what is the stopping criteria for the algorithm? There are 3 options to choose from. We can stop the algorithm if the centroids of newly formed clusters are not changing. Even after multiple iterations, if we are getting the same centroids for all the clusters, we can say that the algorithm is not learning any new patterns and it's a sign to stop the training. Another clear sign that we should stop the training process is if the points remain in the same cluster even after training the algorithm for multiple iterations. Thirdly, we can stop the training if the maximum number of iterations is reached. Suppose we have set the number of iterations as 100. The process will repeat for 100 iterations before stopping. In some cases, if the initialization of clusters is not appropriate, k-means cluster results may not look good. This is where k-means plus plus algorithm helps. It specifies a procedure to initialize the cluster centers before moving forward with the standard k-means algorithm. Let's take the example of these same 8 points. And let's say we want to make 3 clusters. The first step is to randomly pick a data point as a cluster centroid, as depicted by the green point in the second image. Now we will calculate the distance of each data point from this centroid. The next centroid will be the one whose squared distance is the farthest from the current centroid. In this case, the red point will be selected as the next centroid. Now to select the last centroid, we will take the distance of each point from its closest centroid, and the point having the largest squared distance will be selected as the third centroid. Thus, we will select the last centroid as the blue one. We can continue with the k-means algorithm after initializing these centroids. Using k-means plus plus to initialize the centroids tends to improve the clusters in terms of DUN index we just discussed. Although it is computationally costly relative to random initialization, subsequent k-means often converge more rapidly. One of the most common doubts everyone has while working with k-means is selecting the right number of clusters. So let's look at a technique that will help us choose the right value of clusters for the k-means algorithm. Let's take the customer segmentation example that we saw earlier. To recap, the bank wants to segment its customers based on their income and amount of debt. Here we can have 2 clusters which will separate the customers, as in the first case at the top right. All the customers with low income are in one cluster, whereas the customers with high income are in the second cluster. We can also have 4 clusters, where one cluster might represent customers who have low income and low debt. Another cluster is where customers have high income and high debt, and so on. There can be 8 clusters as well, and similarly we can have more clusters. But how can we define the right number of clusters? One thing we can do is plot a graph, also known as an elbow curve, where the x-axis represents the number of clusters and the y-axis represents an evaluation metric, for example inertia. You could choose any other evaluation metric like the DUN index as well. We will start with a small cluster value, say 2, train the model using 2 clusters, calculate the inertia for that model and plot it on the graph. Let's say we got an inertia value of around 1000. Now we will increase the number of clusters, train the model again and plot the inertia value. When we changed the cluster value from 2 to 4, the inertia reduced sharply. This decrease in the inertia value reduces and eventually becomes constant as we keep on increasing the number of clusters. Thus, we will get a curve which looks like a human arm with an elbow. The cluster value where this decrease in inertia value becomes constant can be chosen as the right cluster value for our data set. Here we can choose any number of clusters between 6 and 10. We can have 7, 8 or even 9 clusters. You must also look at the computational cost while deciding the number of clusters. If we increase the number of clusters, the computational cost will also increase. So if you do not have high computational resources, it is suggested to choose a lesser number of clusters. Time for hands-on practice using Python. I have provided a link to the Jupyter Notebook placed on GitHub in the comments section of this video. Let us now turn to the Jupyter Notebook to see the code in action. We start by importing the required libraries. This command directs matplotlib to display generated plots directly within the notebook itself in line with the code cells that produce them. And we import the k-means class from the sklearn.cluster model. This command loads a CSV data file available online related to wholesale customer data. Data.head command displays the first 5 rows of the newly created data frame data. This is a common practice to quickly inspect the contents of a dataset and get a sense of its structure and data types. In this dataset, we have the number of items bought by various customers. Data.describe command generates descriptive statistics. It helps us in gaining a quick understanding of the distribution and central tendencies of numerical variables within the dataset. It also helps us identify potential outliers, unusual patterns, or data quality issues. The scalar command is used to standardize all the features of the data. This method calculates the mean and standard deviation of each feature in the data. Then it subtracts the mean from each data point and divides by the standard deviation. The result is a new data frame called data underscore scaled with the same shape as the original data, but with the features scaled to have zero mean and unit standard deviation. And then again, we can look at the descriptive statistics. This command specifies the number of clusters as 2, while this one sets the initialization method to k-means plus plus. And this command fits the k-means algorithm to the scaled data. This command calculates inertia based on previously run k-means algorithm. This command creates an empty list named SSE to store the inertia values for different number of clusters, and it iterates through cluster numbers from 1 to 19 inclusive, and then it appends the inertia value of the current model to the SSE list. This creates a data frame named frame with two columns: cluster, which contains the cluster numbers 1 through 19, and SSE, which contains the corresponding inertia values. This command creates a figure with a specified size, and this command plots a line chart of inertia SSE against cluster numbers cluster using markers for each point. And finally, these commands label the x and y axis. On running this code, we get the elbow curve. And we can say that from cluster number 5, the inertia starts to stabilize, so we can choose 5 number of clusters. We again run the k-means algorithm with 5 clusters. This command uses the fitted k-means model to predict the cluster assignments for each data point and store the predicted cluster labels in the variable called pred. This command creates a data frame named frame from the existing scale data, and then it adds a new column named cluster to the data frame, which stores predicted cluster labels for each data point. And finally, this command counts the occurrence of each cluster label in the cluster column. It adds a new column named cluster to the data frame. This column stores the predicted cluster labels for each data point as obtained from the k-means algorithm, counts the occurrences of each unique cluster label in the cluster column. This provides information about the distribution of data points across the different clusters. It returns a series object where the index represents the cluster labels and the values represent the number of data points assigned to each cluster. Since this is a multi-dimensional dataset, we cannot visualize the results. I have provided the link for a code for visualizing the results for a two-dimensional dataset, the same dataset we talked about in the beginning with income and debt as the two variables. I have also provided the link to this dataset in the comments section of this video. As you can see that we can create 3 clusters and also display the centroids as red dots. It is the end of this video. Thanks for watching.